Today we're going to discuss the orbits and their geometry in the system we call the sophomore physics Earth. And the orbits are being done mostly inside the Earth by the neutron starlet that is acting as though it were orbiting in a vacuum with the somehow the oscillator field that is produced by the sophomore physics Earth causing it to move. So what I wanted to do is show you a couple of different constructions. A fairly old construction that's borrowed from Kepler's construction of Coulomb orbits. Works very nicely and is very quick for certain situations, but the general construction that works for any possible initial conditions of a two-dimensional harmonic oscillator is the one that's based on phasor clocks. And this is a really important geometry to learn because it ties into the quantum mechanical two-state system. And the quantum mechanical two-state system is two phasors, a psi1 and a psi2, each with two real components. So that's a four-dimensional phase space. And so what we're doing here is useful for a lot more than just this fictional stellar orbiting.
I have a question. Phase space is a plot in XP space, right? Position is a momentum.
Yes, we're going to describe that. That's something we haven't said much about, but it's position versus velocity.
Okay.
Or, actually, Poincaré's invention was position versus momentum.
Right. But in quantum mechanics, we don't know exact x position and momentum simultaneously. So what is
but the phasor is something that we can at least claim some measurement at precision with. The imaginary part of a wave function is proportional to the velocity that is the real part is undergoing. So we're talking about motion in a space that underlies what we normally think about when we learn quantum mechanics. And again, this is something that Feynman made a point of, is the little phasors that are clocks that are keeping track of space and time around a wave function. So we're doing it here for a very simple classical problem. Two-dimensional isotropic harmonic oscillator, that's what the I stands for here. So the two different constructions of this, and then the energetics and momentum and angular momentum that comes with these orbits, they're quantities that are often constant, particularly the angular quantities. And while we're discussing this, I would like to just give the answers for the Coulomb orbits, that is, the orbits that live outside of our sophomore physics Earth. Now, let's remind ourselves of the potentials and the forces that are existing at a certain distance from the sophomore physics Earth. We constructed the potential, in this case, just minus 1 over x. That's this curve right here, which would, if the Earth weren't starting here, if the uniform density of the Earth were starting there, it would have continued down this way. I'm just guessing where it would go. I'm going to ask you to go ahead and finish the geometry for that. But as you know, 1 over r, or 1 over x, goes to minus 1 over r, goes to minus infinity when we reach the origin of this. But the Earth takes over, the sophomore physics Earth, being uniformly dense, produces a perfect parabola. That is, the potential of an oscillator. The potential associated with, and here's the force that goes 1 over x squared with a minus sign, to this point here, and then abruptly, in the sophomore physics, Earth changes direction, doesn't change value, but it sure as heck changes derivative, and then has a constant derivative from there on up. So this force right here is the outside, and inside it's simply equal to minus x. The spring constant is 1. And then this one here becomes a minus 3/2 plus 1/2 x squared. So these are the force and potential that we're dealing with, and today we're mostly dealing with the inside of the sophomore physics Earth. Okay, so these are the guys that we're worried about mostly today. Okay, now in the description of this in the text, this is in chapter 9. Description of this in the text, we start out by finding the most pedestrian way we can to derive this phasor geometry, this a sinusoidal motion that is associated with an isotropic harmonic oscillator, F equal minus x. And the idea is that in one dimension you have probably a pretty good feeling for it, but we're going for 2, and this is applicable to 3 dimensions because the orbits that you will make in the 3-dimensional inside of the Earth will be ellipses that live in a plane. So all you have to do is orient yourself with that plane, and that will be really a 2-dimensional problem. So each dimension, x, y, or z, obeys the following energy expression: kinetic plus potential. But it's all 3 of these together that would work on this problem in general, and for any given orbit we can reduce this to a 2-dimensional problem. So this is what I'm saying in the next thing here. The equations for the x motion will be given here first. They apply as well to the dimensions y, where there's a velocity y, and z, where there's a velocity z. In the ideal, and I emphasize the letter I here, isotropic means that no matter what direction I look inside here, it's always the same. So this orbit could be a 2D or a 3D orbit. The paths are always 2D ellipses if you view them from the right angle. Now, what we're doing here is we're playing the old game that we played before when we turned the Lagrangian into a Estrangian, or the Hamiltonian going backwards into the Estrangian, sort of the halfway point. We do that again here with our kinetic energy, mv squared over 2e and kx squared over 2e. This is recognizing a incredible symmetry that an oscillator has. The idea that both the kinetic energy and the potential energy are a quadratic, that is a square of the particular dimension, either position or velocity or momentum. So I'm simply writing this thing in a way that lets me get a sum of 1 here. I've divided through by the energy, and factor 2 is on both of them. So I can write this thing as 2e over m. This one is 2e over k. And there's a velocity, which was squared before, and there's a position, which was squared before. And this is adding up to 1, so I can assign an angle as a single coordinate. This is called the action angle in advanced mechanics, but why wait for that? It's a very simple trick that we do. Once again, another example of the old scale a circle trick if you have an elliptical object. You can always just generate some more dimensions. If you have a hyper ellipse of some kind and it's positive definite, you can scale its hypersphere. We'll be doing some of that later on. So anyway, the first thing is this velocity. Here is then 2e over m square root times the cosine of theta. That's this guy right there. And the position is given by this thing with a sine theta. It's not 2e over m, it's 2e over k. So that lets you solve this equation, and it's the simplest solution I can think of. Doesn't require knowing calculus, although I'm using calculus notation for an angular velocity. That's what I'm going to add to this thing, is besides a linear velocity, we have an angular velocity, the d theta dt. But the idea is that this object, this pi 1 right here, this v, that's the linear velocity dx dt, and that's the same as d theta dt times dx d theta. So these two cancel each other. That's sawing a derivative in half or something. We're going to do some more of it with partial derivatives fairly shortly in our discussions of the mechanics later on, the geometry, what I call quadratic form geometry. So anyway, we have d theta dt, that's what we call omega, okay? And I can then rewrite this just by using this here. I can rewrite that with our omega, this dx d theta, and that's this guy right here, dx d theta. Here's where you have to know that that's the cosine. So here's something multiplying a cosine, here's something else multiplying a cosine, but with an omega. So that gives you the omega. The omega d theta dt, that's this quantity here, is constant. Now that's the key idea, is that there is some sort of clock. That's what we're making here with this trick, a phasor, if you will, and the motion that you're going to see here for all of the quantities, velocity, position, their derivatives, including acceleration and jerk and other force derivatives and so forth, are all going to be sinusoidal. That is, they're all going to be matched by this equation right here, this constant derivative, velocity, angular velocity. This theta, the integral of omega dt, for a constant omega is simply omega times t, plus whatever initial phase angle you have. So that's the basic idea of any one-dimensional oscillator. And now with two, you see this is a one-dimensional oscillator. Here there's position, and then a velocity divided by omega to make a circle. That's the key to this, the geometry that we're going to do here. And we'll use it later on when we talk about normal modes and all of that sort of mechanics, regular classical mechanics. But be aware, this is the coolest way to understand a lot of quantum phenomena, relativity too. So this is a very crude construction here where a clock is allowed to run and this one is allowed to run. And the idea is to build some graph paper off to the side here where you have the x position this way, and that takes care of the dimension x in a two-dimensional oscillator. And then dimension y, there's the y position axis right here. So you have a phaser here that's oriented the way we usually do them when we're talking about complex numbers. And this is something that we'll take up in more detail in the chapter 10 of Unit 1. But this position and velocity, this is the real part of something that's oscillating. This is the imaginary part, this whole thing with the omega making a circle. So we're conflating a lot of different developments of mathematics to pull this off. But you can see the basic idea is that if this one's at 1 o'clock, well, this one is at 3 o'clock, and that's the way to think about this, is 0, 12 o'clock, 1 o'clock, 2 o'clock, 3 o'clock. This oscillator is going to tick through the hours. Well, this one ticks through the hours at exactly the same speed, omega. They're both in this isotropic oscillator together, doing their oscillations at frequency omega. Single frequency is isotropic. Doesn't make any difference what direction you take, that's what you're going to see. And the idea, of course, is to note which oscillator is ahead and by how much. We call the phase of this oscillator, it's reading in as a clock. 1 o'clock, 2 o'clock, and 3 o'clock. So if I happen to have started this one right at this point, that is, I picked this oscillator to be at 1 o'clock on its phaser, and this oscillator to be at 3 o'clock on that phaser. Now, this is a clock that's a little different from what we'll use later. I'll use a clock that has 12 hours. This is an 8-hour clock here, when the period into 8 places. But anyway, if there's the coordinate, you see, of that ellipse. And that means in the next step, next tick, this one has to tick over to 2, and this one has to tick over to 4. So putting those two lines together is the next point on the orbit. Then this one ticks to 3, okay, and the other one has to tick ahead too. It drops down here to 5, you see, so that's the third point, and so forth, all the way around this orbit, you see. So this is a very simple diagram of what's going to happen inside the Earth. It's going to make an ellipse that's generally tipped by some amount. So that's the idea. Now, phaser clocks with positive, I should say, energy, positive mass, if we're talking about quantum mechanics, they're all left-handed. And the reason for that is that if you're up here with a positive velocity, there's only one way you can go, and that's toward positive position, assuming you have a right-handed coordinate system, x and v. So the clocks, both of these clocks, always, and everything we'll do here, have positive frequency. That is, they use the left hand. Okay? Now this particular orbit that's going this way also is left-handed. But if instead of picking, I had two choices here when I picked this thing to be at 1 o'clock, right there, I had to be somewhere on this line. I could have been here instead of here, you see. I could have already been at 5 o'clock at that particular juncture, you see. So if that were the case, then this is the orbit I would get. I would get a right-handed orbit going from there. So these will always be turning this way, but this can go either this way, left-handed, or it can go right-handed. So that's a little bit of freedom that these, otherwise this mechanics is very rigidly determined. Okay, they also can have different amplitudes. They can be at 90 degrees phase lag. This is a 90-degree phase lag, producing a circle if the two phasors are the same size, producing an ellipse that we're used to, a kind of ellipse that's horizontal, the x squared over a squared plus y squared over b squared ellipse that's horizontal. There are two very simple examples of a phase of 90 degrees. If the phase is 0 degrees, then you just get a straight line, y equal x. Or if it's 180 degrees, you get a straight line going the other way. So this is the basic geometry of elliptical orbits. Now, another description of this involves the phasors still maintaining right angle projections with each other, but at some angle. So it might help just to, while we're going through this geometry in a very laborious fashion, to realize that once you have a phasor here that has an x coordinate here and this velocity coordinate vx up this way, and another phasor down here that has its y turned sideways so that the y and the x can project to the points of the various possible orbits in the xy plane, you can at the same moment track the velocity trajectory. I'll show you a trajectory in just a minute here in detail, but here they all are together, different possible settings for these phasors relative to each other. They will produce various ellipses that fill up, in this case, a square, because I've made the amplitudes of these two exactly equal. So, TC, maybe if you wanted to go ahead and get the diagram in for you. Those of you that would like a convenient way to do the problems associated with this that are going to come up later, here are two, I'll just give them two different kinds of graphs. Take one of each. And you can see what it is. This is very much like the one that doesn't have much written in the center, so it allows you to do some constructions of the size of the circles and the phasings there. But you see, the basic idea is that you're given an initial position, that's two numbers, and an initial velocity, another two numbers, okay? And this is on a graph, and you can see the tick marks on the side here, 1 through 10, minus 10, 0, and then 1, 2, 3, 4, 5, 6, 7, up to 10 for velocity, same thing for position.
So, so are the two axes Vx over omega and Vy over omega? Are they two?
Yes, in order to get a phasor that goes around in a circle, we have to scale it, right? And if you have a cosine of omega t this way, which you do, then the velocity that's associated with that is the derivative of the cosine of omega t. Well, that's minus omega, right, times the sine, right? So, the minus sign makes the thing go left-handed. That is, it drops to start with. Your hand, if your clock hand is here, it goes this way, right? That's the minus. And then the omega would have changed the this thing to some other value. If omega was high, then I'd have an ellipse that was, like that, right? Or if omega was below 1, I'd have an ellipse that was like this, describing velocity and position. I need to divide by omega to keep it a circle. Get rid of that extra factor. Does that make sense? And then, and this is another tricky part, when I do the y, I've got to rotate by 90 degrees so that I can get x and y here. And then when I do that, you see, I get Vy here and Vx there. You see, look at this thing at 90 degrees, and I see Vx and Vy, both divided by omega. So we get both at once. So if I'm given, let's just take omega to be 1 here so you don't have to worry about those factors. If I'm given the initial value here of -8 and +5, okay, so that's your initial velocity, right? And then your initial position is given by +7, okay, so here's 0, +7, okay, and then up 3, then that tells you all you need to know what this is going to do forever. Okay? So what we do with these is we locate a point up here, the intersection of these two, and this is unambiguous. I've got this thing over here. Anything along that line would be also giving this point, but we've specified that one right there giving this value right here for this phasor. So this sets two phasors. The line across here intersecting that line, okay, that's one of the phasors. And then the other one is this vertical line intersecting that horizontal line right there. And then from that point, we draw a clock. That's our phasor clock right there. And then it's just a matter of bisecting and trisecting 180 degrees to get finally 12 divisions. Every half hour, if this were an hour clock, is now marked off by these blue lines. So that's your ticks. We can make them finer, but that's fine enough usually to get a pretty good curve down in this region, and then another one right here. So we're going to be getting a very special ellipse here and a very special ellipse here. Now this geometry has a name in optics. It's called ellipsometry. And it is one of the most powerful spectroscopic tools that we have now for looking at complex objects such as molecules and solids. So when you're thinking about a state of polarization, say EX and EY, there's a very good description. We need to get a convenient coordinate system to characterize an ellipse. And we already have it, a Cartesian coordinate system with these guys, but most people, for some reason or other, don't think that way. What we need is a way to characterize that, and that eventually is what we'll do. But here we just want to find out what the ellipse is. So this thing ticks to the next point. I've just shown a very thin initial condition here and a thin initial condition there. So I have ticked, you see, from this initial value right here. This would be 130, I guess, if I was looking at those clocks. But anyway, whatever that particular point there is the new phasor clock, and it's going to intersect with the new one over here. This one had to tick from here forward to there. Okay, and let's see if that is right. Yeah. So our new point is the intersection of this line with that one. Okay. And then the new velocity point here is the intersection of this one with that horizontal line right there. Okay? So this was the velocity we started with, this is the velocity we end with after the tick. Those vectors placed over here should be in the direction this thing is going. Well, it's not quite, because neither one of these has the velocity that would really represent the average between these 2 points. But that vector right there, or this one, okay, Now you've got to rotate it back, you see, by 90 degrees is this vector. So I'm just drawing the velocity vector where it would be on the ellipse that we're trying to make here. It's in the right direction. But that's the exact magnitude and direction of the velocity in Vx, Vy over omega space. And this is where it is, that's x over y space, configuration space you could say. This is velocity space. Most two-dimensional, of course. Okay? So, usually x and y phasors have unequal size, and this is only slightly true of these. These are pretty close. But the most interesting ones have equal size. As you'll see, that's called fully saturated oscillation. So I'm going to the next tick, okay? Next tick is this one right here, okay? And when that occurred, so did this. This one moved up, okay? This is our new velocity, linear velocity, based on these two phasor motions. And then the position motion is now over here. So this vector, rotated by about 90 degrees, is somewhere between the last one and this next one. Okay, it's about there. Right? That's what's going on. We're doing a very discrete integration. Next tick. Next tick. Next tick. Let's make some pretty big jumps right here. Next tick. Next tick. And that's all I've done on this particular one. But basically what we did is we traced an ellipse up to this point, and then here is a long section of an ellipse for the for this particular interval. Now what TC has on the screen over there is a picture of the thing in motion, and it isn't the same as this one, but it's the same basic idea. And that isn't too far from an ellipse that this would draw. And the circles, of course, are a different angle as well. The two phasor circles that are driving this particular guy are on one side or the other. Those are the red ones that are making the ellipse inside there.
Should remove the red ones, red.
So
I should remove
now this is an ellipse that's going right-handed. This one is going right-handed like he's got over there, but notice the phasors, of course, are going always left-handed, just by their definition. Now to make it go left-handed as well, he flipped it by the phase by pi over 2 there, and now he's making an orbit. You can erase the path so you just see this one. And there's an ellipse that is got a left-handed turn to it. Left elliptical polarization if you were talking about optics. But this is the same mathematics that you use to describe any two states in a quantum system. Pick any two states, and if that's all it's going, then this is the dynamics you see. The beats, as it were, of the two levels. Now these levels are degenerate. That is, they have the same frequency. The state associated with this phasor is the same frequency as the one associated with that. Obviously, we're going to return to this in Unit 4 to describe normal modes where they don't have the same frequency. And that's where ellipsometry gets interesting, because then the ellipses start dancing, you say. And it's from that dancing that we determine the properties of a lot of crazy materials.
Just Undo the normalized phasors.
Okay. Now, I'm going to go back to this, just run through this thing real quickly as going backwards. But this particular object here, there's a very skinny ellipse that has been asked to go around the corner here. I'm going to ask you to construct some things like this using whatever graph paper you want to use, but I recommend the one that has lines on it like this. You can really just plot the thing directly. But there are two ellipses that are related to each other through derivative. And that's what we need to do, is we have to look at the calculus that goes with this vector geometry. This is a case where the geometry can be a little confusing sometimes, and the algebra helps you out to see exactly what should be your construction. So, go through this one more time. Tick, 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 and part of an ellipse. Okay, now, here's another construction. This is the construction that you would use if you were sure that the ellipse was horizontal. If you want to make a horizontal ellipse, and it is also perfectly suited for making a vertical one, where the major radius, or the major semi-major axis, or the major diameter 2A is bigger than the minor radius B, also called the semi-minor axis, or the minor axis is 2B. The minor diameter is 2B. Those are the two numbers that describe an ellipse if you know that its major and minor axes are in X and Y. So the question is, how do you construct this very quickly on graph paper? And the answer is, you simply draw the circles associated with the minor and the major axis. And then it's pretty easy. What you do is you just pick an arbitrary, this is called Kepler's mean anomaly line in his construction of Coulomb orbits. It has a slope angle given by the angle theta, and the theta will actually be omega t. And we can prove that very easily by just looking at the algebra of x equal a cosine omega t and y equal b sine of omega t. We get both of those at once by drawing that line and seeing where it intersects the B circle. Then that right there has to be the value y equal b, the hypotenuse, times the sine of the angle that little, it's like a phasor clock, it is located. And it's going along at a uniform rate, dragging this point up by that much, namely b sine omega. Meanwhile, and this is the thing that's neat, you extend this line all the way to the A circle and drop a perpendicular. You don't have to drop anything if you have graph paper. You've got both this line and this line easily located. You simply find their intersection by eye. You don't really have to draw anything. This is a construction you can do with just a ruler. You know, except for drawing the circles, you don't need any more curved constructions, you see. So this starts off right at this point, where the point is just located at the intersection of wherever that is and wherever the other circle makes a sort of a heel, and it drags this thing up. This thing gets ahead of the actual radius that is the orbiting particle lies on. So, you can see what's going to happen as I get closer and closer to here. This has got to catch up. You see, it's always underneath it. And finally, when they pass right at this point, this thing is going really fast, much faster than this point. That is, the radius is much faster in this region. Well, you're familiar with that as the speed up that you get in an orbit at its perigee. At its apogee, it's going fairly slowly. You can think of a particle starting here and falling along this curve. It's obviously going to speed up. And then from there on, it's going to slow back down just symmetrically to what was rising until it goes zoo and then slows down right here. It'd be going slowly past that point, just as it was going slowly past that point in the beginning. So the geometry gives you a very precise description of what are called Kepler's laws. That is basically equal area swept out. And that's what we need to discuss, all of these laws for central forces. And this is one that's true for all the central forces, but we're going to consider two very special ones, the ones that go with the sophomore physics Earth, namely the Coulomb 1 over r force, 1 over r squared force, 1 over r potential, and the oscillator, which has the Hooke's law force with a parabolic potential. So here's the steps for what I just said. Draw concentric circles of radius A and B, radius OA at some angle. Pick a time, in other words. This is giving you everything exactly in time, just like the phasor construction, the dual phasor construction does. But this one's quick, a very quick way to get the orbit if you know where its apogee is, and you treat that as your x-axis. Okay, so all you have to do on this is draw one line down from that that's giving you an x coordinate in a y direction, and then do the same, draw a line across, okay, and there's your intersection, okay. So it's the intersection of horizontal and vertical. Both of those lines are on the graph paper, so you don't have to construct anything. You can just sort of eyeball it all the way through once you see where this line goes. Okay? So that's the Kepler construction for this. And this is just showing a couple of points. And you have to realize, you see, that the particle actually traveling on that orbit is tracking another particle that's in a tunnel, say, falling straight to the center of the Earth and coming back out the other side. These two will go in synchrony, always being directly above each other. So right here he's going to be going pretty fast because this one is in the center going as fast as he ever goes. This is doing the same. He's got exactly the same velocity in this direction at that point. And then this one starts coming back down to meet it, slowing down his extra velocity to match the x velocity of the particle going straight. So this is the analogy of the famous shoot the monkey experiment in sophomore physics, where you imagine, well, most simply, is a gun shot straight out, bang, and goes over and falls on the floor at the end of the room, and I drop a bullet at the same time, right? And the y coordinates track each other, so that it hits the floor exactly when the one I shot hits. It's the same, almost exactly the same thing, except it's being done with elliptical orbits inside the sophomore physics Earth. Is that all? Check with what you already know. That's it. You know, the key part of all of this new stuff is to make sure it connects with what you already know. So let's look at the calculus of this. This is quite amusing, I think. Let's look first at the position vector. Okay, here's the radius vector. R sub x, R sub y is a clumsy way to write x and y, but if you're letting this be a vector, then that's what you do. And certainly with velocity, the linear velocity, we write vx and vy for the Cartesian coordinates of it. So we're having here an x, which is a cosine of omega t. So that particular phi equal omega t, that the so-called eccentric anomaly, or I should say the mean anomaly. The anomaly just means radius in Kepler's language, and astronomers use it to this day. This is the mean, because it's going at a speed that is the average or mean velocity of the actual particle in trajectory. So a cosine omega t, b sine omega t, just like we said before, a cosine phi, let's say, now I forget the time briefly. So the phase, we're talking at a phase angle here, or time frame angle, phi equal omega t, called the mean anomaly. And the position vector r and the velocity vector r are connected. We take the derivative of these two functions with respect to time, and we have here a minus a omega sine omega t. I'm taking the derivative of that thing, and then this one comes out with a positive sign. Again, both have omega in front of them, and they both have a radius a and b. Okay? Well, you notice that this thing right here, this minus a sine omega t, is really a cosine. Okay, cosine of the omega t plus pi over 2. And this one right here is a sine of phi plus pi over 2. So all that's happened is I've taken a vector here and I've run the phase angle up by pi over 2. Okay? And we're going to be letting the omega disappear for a while, make omega be our unit angular velocity. Okay? So the idea is that this mean anomaly angle of vector v, okay, well, it's the same function. It's just that I've advanced it by pi over 2. Let's do it again. All right. Well, that will give you the second derivative of this vector, the first derivative of this vector. Okay, so I go through here, take a derivative of this thing to get a cosine. Another omega, if I add something besides 1. Same thing here, I take another derivative of this. This gives me another minus sign. So I get a b cosine sine. Okay, that's the acceleration. Okay, that's the same function that we had before with the polar angle advanced by pi. Here is the position, there's the acceleration. Well, that makes sense because we have Hooke's law here. This thing extends out and it has a force, a physicist force, that points negatively to that. The force is minus spring constant times distance vector. So there is your acceleration. Okay? And you see the little triangles that are associated with that thing. Now, another derivative. Okay? Jerk, or change of acceleration. All right, that's NASA's terminology. It was instituted in shortly after the kernel stamp experiment that we talked about before. They also worried about what the effects of change in acceleration are. They are very often even more devastating than the acceleration. But that idea that I would then advance the angle by another pi over 2. So that's what's happened. These things that determine the mean anomaly is just a Cartesian coordinate system. The other things follow along on this ellipse with a little foot there with the actual position vector always on the heel that's hanging down. Okay, and that's the Kepler construction.
I have a question.
Yeah.
What is the physical meaning of jerk? For example, I can feel acceleration or velocity, but I don't know what is jerk.
Let's say it's what would upset you if already you were in some sort of rocket mechanism, you know, that was really making you heavy, right? And if somebody suddenly changed that, your weight, your effective weight, the rate with which that changes is what you would feel.
We're like an elevator.
You know, you have to experience jerk in order to change your acceleration, right? You're going to have a negative jerk to get rid of the acceleration and come back to, you know, being in a more or less inertial frame, right? So it deserves a name, and it definitely does. And the idea of being jerked, you see, is I'm changing the acceleration of you. I guess is what they were thinking of. So, well, two can play the name game. I also have a name for change of jerk. This is not in the NASA Dictionary of Astronautics. This jerk is in there, but this is not. But I'd say change of jerk, and all the Republicans would agree with me this time that there was a change of jerk at the inauguration. But I don't agree. I don't like this anymore because I don't think Obama is a jerk. I think that we made the change from Bush to Obama. That was a change of jerk. So you see, once you've gone all the way around, you're back here. Now you do any more derivatives, 4 more derivatives, you just go around the circle again. So we won't play that game anymore. But it's interesting just to see this thing in motion. You see, as he's dragging the mean anomaly around, at whatever rate you feel like letting time go forward, these are the 4 points of our dynamic compass. It's worth knowing about these for any system, because every system can be Fourier analyzed, and each Fourier component will have one of these. So you have here position, velocity, acceleration, and jerk. Those are the 3 things that you work with in mechanics. And the oscillator is particularly nice in the sense that for this, they're all the same, roughly. They have the same geometry. They're sitting there somewhere on Kepler's thing. So what it's saying is that this particular velocity here is a position in the future. When that's the position, this will be the velocity, and so forth. Because of that wonderful symmetry, we get to use the powerful mathematics associated with complex numbers for doing complex variables. So that I think is a neat lesson. It's where we can, you know, combine the calculus and make a roadmap for it. This is a roadmap for what would otherwise be things that you wouldn't maybe be able to picture or appreciate as much. Okay, is this so far so good?
Just want to read your notes once again.
You're right. The act of putting a geometrical something or other together with the formulas that describe it is not automatic. Your visual system is very automatic. It can see you know, patterns emerging. One of the things that's really, I think, quite striking is the optical illusions associated with this kind of motion. Perhaps you can show that fairly easily by looking at the previous construction, which was just a couple of oscillators. Go back and just do the couple of oscillators again. And go ahead and let the thing run with all of the position, velocity, and jerk turn on. So go ahead to the, you remember how you put in those vectors on this program, and I forget where that is. Show the what I'm thinking of is where you show these vectors actually in motion, right?
Yeah, I had to do that manually.
Yeah, this is something else we're going to be talking about later when it comes to the quadratic forms.
This is where we were.
But the what I was thinking of were the thing where you actually draw these vectors, first derivative, second derivative, third derivative, and so forth. Do you remember that?
Sure.
See if I can think where it is. Go ahead and get this thing in the finder here, and I'll look for it. I'll just get the old one.
You're saying it's in box it?
I'm really sure of that. I'm really very sure of that. And I think yeah, that's it. See if I can. Yeah, here it is. So this is the old version of Box, and I'm sure this, that you put this, just, we've done so many things to this, you may have forgotten it, but let me go back here and do off-screen animation, but not with all that going. Let's go here and reset the parameters. So that I have an isotropic oscillator.
Yes, we do have derivatives.
You do have that?
Yes, we do. This is it. You don't need to search any further.
I'll go ahead and run with two vectors. Whoops. And I think it's doing something more than I want right here.
Here it is, Bill.
You got
Sorry
it?
about that. Yeah, I just
Okay.
hadn't discussed it for
Yeah.
class, so it wasn't in mind.
Yeah.
You can see where
Now, remember we discussed perspective. That is the ability to draw on a canvas, a two-dimensional canvas, something that has depth by doing basically the zigzag construction that gives you lines. Now, tell me if you don't see that blue circle coming out of the screen or into the screen. Forget that it's the Kepler orbit that has the ability to gain speed and lose speed. Now gaining, now losing. Now it's slowest. Now gaining speed. But yet, the thing that you see there, your mind says, that's a disk rotating out of the screen uniformly, right? And indeed, the projected phasors are turning uniformly, right? Yet the object that you see in your mind, this is where the mind makes a mistake, but it's it does that for a reason, because you want to, if somebody's swinging a rock at you, you want to be able to see that it's coming to you, right? So you evolved with the ability to see a three-dimensional object on a two-dimensional image like that. That's what's called an optical illusion, a dynamic one in this case. And if you make that even skinnier, that ellipse even skinnier, just go ahead and give it a little bit of a thing and erase the other one. Then zoom, there's the thing ripping past the perigee. Now it's at the apogee, or they call it apogee. Now it's coming back to the perigee. You see?
It's exaggerated.
So the speed is definitely changing. Do a big one, yeah.
Here is path. We start.
So all it looks like, and you could do this just with that disc alone, forget the phasers that are making it, they very clearly show that this is a uniform oscillation, uniform frequency, and constant angular velocity oscillation, but the object appears to come out of the screen now, or into it, but out of it for me in this particular, that's what I'm seeing anyway. So, you'll see this if you're looking at the beam of a lighthouse. The lighthouse, you know, is over here for a long time and then goes right by you and then slows down again, right?
In that simulation, the ellipse is in a plane parallel to the ground, right? Like it's like if I.
That's what it looks like.
Yeah.
But of course, it isn't.
Here's what it would be if it was perfectly horizontal. I just set it there and released it with no tangential velocity.
Now, you see,
It's right on the
it
edge.
comes to a complete stop there, and then it speeds up.
It's a aristocrat.
Yeah, speeds up right there. But the thing that you were seeing before looks to you like a plane more or less parallel to the floor.
Approaches.
Yeah, a circle more or less parallel to the floor, uniformly rotating. You see, no Kepler speed up, no Kepler slow down. But that you of course have that velocity. So that's part of this story that I think is rather amusing. Definitely a good thing to know about. Okay, I'm going to switch this one back to the now the thing that we would like to do is notice in all of this motion things that are constant. The so-called Kepler's laws are just one of those. But before I do that, I want to point out, I apologize for a confusing introduction to Coriolis centrifugal force geometry. Coriolis and centrifugal force and various things that have to do with spherical motion, in my opinion, are very badly taught. But I'm going to back into this improved way of talking, simply to make you realize that it's a pretty complicated idea. And we're going to derive rigorously in chapter 12, which is pretty close to the next chapter after this. We're going to skip 10, the complex variable stuff, first, and get right to the mechanics that makes a lot of sense out of this. The quickest way to compute them, too, and think about them as far as I'm concerned. I think you'll agree. But I want to show you some confusing ways of looking at Coriolis force. First, a not so confusing thing about comparing somebody orbiting in a sophomore physics Earth. Suppose somebody has simply dug a hole so that something besides the neutron starlet can enjoy a voyage around the Earth just under the surface of the Earth, or anywhere in here, right? And the idea is, what would you, what would it be like riding on a capsule that moves frictionlessly along some sort of maglev support system or something that goes all the way around the Earth? are all the way around some gravitational body in the near, far, far Star Trek future. And I think that you have to agree that the Earthronaut, or whoever it is that's orbiting at this low-level orbit, I mean really low, below the ground, but it's in a tunnel, so he's not feeling any force. He says, this is great, I'm weightless. Okay? Contrast that to the, I call the carnival kid, that is on some sort of amusement ride that consists of you at the end of a spring. You got some sort of thing that's flinging you around, and let's suppose that they're flinging you so that you have a constant angular velocity. Okay, same centripetal force due to the spring, and you're holding on. This is awful. I can hardly hold on to this darn spring. Okay, certainly feeling your weight, right? As you go whizzing around, you know, like that on this merry-go-round, okay? And but it's the same force that's acting on this object right here. It's just that the gravitational force, this is what we call centrifugal force, center fleeing force, okay? Centripetal center pulling force. Those are the two opposites that are in action here.
I have a question. Is centrifugal force a real force, or is it like a pseudo force that we just define to explain?
Your question goes right back to mathematician versus physicist, right? For every force, which is a flow of momentum, right, there has to be somebody that lost momentum, right? The counts have to add up, right? So for every force has to be equal opposite.
Right.
This is Newton's third law, right? I think.
Right.
Who's counting?
Right. But
Okay.
I have a doubt like when I'm moving in a circle with
Yes.
a uniform velocity, there is what keeps me on that path is that inward force towards the center, which we call the centripetal force, right? That is directed radially inward. Now, centrifugal force is supposed to be directed radially outward.
Well, what you're feeling, if you just let go, where are you going to go, right? You're going to follow a straight line on tangent.
That's right.
Right.
At every instant, the direction of
But
velocity.
your radius, you know, you're out in the middle of space. So what's going to happen is you're going to see your radius grow, right? So you're fleeing your center, right? That's centrifugal, fugal free, right?
So does it mean that what keeps me on the track is
In order to stay there, that's the physicist's force, right?
Okay, okay.
Okay? The mathematician's force is what does it take you to stay at the same radius? You gotta pull this way, right? Something's gotta keep you toward the center. Center pulling is this one. Okay?
So, so the centripetal and centrifugal force are equal in magnitude but opposite in direction.
Just like physicist and mathematician.
Right. So which means, is that the reason why the velocity is uniform, like the tangential velocity is uniform?
Well, the actual magnitude of this thing depends on your omega. It's quadratic in that, right?
Right.
It also depends on how far you are out. Right? The further out you go, bigger it is, right? Because it will, for the oscillator, be balanced by a minus kx that holds you, right? That's this size right here, which is painless. This is painful.
In which chapter have you discussed this in the textbook, Dr. Harper?
This is from the textbook.
Unit
Okay, this is the
one.
second figure
Oh,
in Unit 1, figure chapter 11.
11, okay.
Okay? Now, we've already talked about this. Mass gaining speed as it falls, mass losing speed as it rises. There's a third kind of force here that is worth discussing. Now, when you look at it from this point of view, it's pretty simple. But we have to have the mathematician force to hold it back, we have the physicist force where the M wants to go if we're somehow released from a situation that we put it in, which is the merry-go-round again, except that this is a nice, we're looking down on something turning on the Earth, so we don't worry about gravity this way. All the forces are going to be in the plane here, okay, due to rotational velocity. And if you get on one of these, and they don't have very many of these things around anymore, every park used to have a merry-go-round that was about as big as half of this room. Some of them were about that big, others were smaller. And you could actually get on the thing, get it going, and go into the center, come out, do whatever you want. Probably fall off, get bruised, and maybe break a few bones. Well, the breaking of bones, we don't like that. So you go to the park now, and there won't be any of this stuff. But you can, if you've ever played on one of these things, you notice that if you go from the outside to the inside, you feel the force on it very, very much. Okay, because right here you're going pretty fast. In toward the center, you're not going as fast because this linear velocity is a product of this angular rate, which is assumed constant here, and for a big merry-go-round it will be constant pretty much, times the distance you are from the center, r. Okay? That's the rotational velocity. And of course we have a small version of that on the Earth. The further you get from the Earth's axis, i.e. North Pole, the slower you are going. So if you're going to have a velocity along a radial path, you find a little track or something that you can push yourself along, you're going to have to slow down, right? To hold you on that track, you're going to need a mathematician's force this way. The physicist's force, that's where the mass wants to go. If you released from this track, is this way, and equal and opposite. And this thing is called the Coriolis force. This one depends on the radial path speed. As I move up this path right here, suppose I'm on a little track on that path, looking at this in the moving frame of that merry-go-round. Remember, it's going right-handed here. Okay, so that's the constraining force to keep you in the slot. That would be the mathematician's Coriolis force, the thing that holds you in place. If the track breaks, where are you going to move? Well, you're going to be drawn this way, right here, as you're going, because you're in a region that's slow now. You're going to make a curve like that. Okay, I told you this was confusing. But this is simple compared to what's happening in an orbit. I say quite confusing. The discussion of Coriolis forces will be done more elegantly several different ways. First in chapter 12, where we just go right to the point and use coordinate systems to solve all our problems. Then in unit 6, after we've done all sorts of problems, we'll come back and look at it from another point of view. That lets you calculate things and understand what the heck is going on here, because you see there's a centripetal force due to the inside of the Earth's gravity, which is just F equal minus some constant, which we take to be 1 in our geometry, times the actual position vector. So here's the position vector pointing this way. The force is exactly the same length, but in, of course, Newtonian units of some kind, but we make the scaling such that it is exactly that length, okay? Then as it gets closer, that force is less. You see, it's really big here, and the force is less, always pointing toward the center, right? Then the inertial force, which you might call the physicist's force, this is the mathematician's force, holding that particle, taking a particle relative thing. This is the physicist's force, this is the mathematician's force, equal and opposite, okay? Now this thing is on a circle for a brief moment. There's always a curvature at every point on here. So treating that circle as something to talk about, then anything that flees the center of that circle is called a centrifugal force. And anything that's perpendicular to that is called a Coriolis force. This is the only force we have to worry about. That's the centrifugal and that's the Coriolis. Confusing? It should be. You need to think this through several different ways in order to really be comfortable with it. Especially when a circle gets small. Okay? There it is again. So we're going to come back to this. This is something that you need to chew on during the whole semester, not something you get done in just a week or so.
Dr. Harter, so have you discussed centrifugal force in chapter 11 of Unit 1?
Yeah, Unit 1 has 12 chapters altogether, right? I mean, I've set it up in there, so they're all available. You have a tab for 11, okay? We're skipping 10, the complex variable stuff, till the very end of this unit. Sort of gives us a little play so we can spend more time on the physics. Okay, now, as I said once again, our first look at this is done in a very rigorous and beautiful way using differential geometry. That's chapter 12. We'll be going at that fairly soon here. All right. Okay, let's finish up here. This is something I can go through fairly quickly, as I want to look at the invariants, the things that are kept constant. All this stuff is changing, you see, as you go around the corners. But I want to make very clear some of Kepler's laws that he invented for planetary motion and Coulomb fields. But this one is good for any central force, any force that does not care about the direction you are. It only cares about the distance you are from some center point. So you can have any function of r. We're doing the isotropic harmonic oscillator, which is only a force that's minus the radial distance. But then there's the potential, kr squared. The Coulomb force is going to be inverse, as we've pointed out, inverse r squared, and have a potential that is inverse linear. So here's the deal. An area of a triangle made of velocity and position. There's the velocity, there's the position right there. So we got r here, v that way at time equals 0. Then it goes off and makes some parallelogram, rhombus, whatever you want to call it. It's a parallelogram, okay? There's a velocity. These are r's. These are all things that we can geometrically construct, or we can go with the calculus that we showed when we were doing this part of the discussion. And then we marry those two. This is sort of one of the results of that marriage. Okay? The idea is that the area of that triangle, which isn't talked about that much, should be, the area of that triangle is constant. Area of the triangle. Area of a triangle. Now, what is the area of a triangle in vector notation? It's r cross v, 1/2. 1/2 of r cross v is an area of a triangle. Okay? R cross v, without the 1/2, is the area of the, well, this thing that you put together from the triangle, two equal parts. All right? So let's look at our, let's just do this by calculus. X and y, a cosine omega, b sine omega for our elliptical orbits. Okay? And then the velocity, remember that, I have my sign up here now because of the derivative of this. All right? Stick those together. Okay? See what r cross v gives you. Okay? And we really need to talk about what a cross product is, too. That's going to come up in our complex variables section. And how does that generalize? That's very important for developing. There's like exterior calculus and stuff that's coming later in your career if you're going to be doing general relativity or something like that. Anyway, look what happens here. Okay? Cosine squared, sine squared, AB, it's AB times omega. That's 1, right? That's the area, AB times omega, basically, is what is showing up in this construction here. This is, all you do is take 1/2 of this, and 1/2 of AB is times omega is the area of this triangle. Okay, omega is constant. Okay, that's kind of neat. Well, if that's true, then so is this. This is our definition of angular momentum. R cross V, sophomore physics definition of angular momentum. Now, cross product, it's a product of the lengths and the sine of the angle between those two. Okay? Well, that's coming out to m times AB times omega. Okay? So that, just put an m on this thing and you've got angular momentum. Okay? So we check off these two constants for the certainly true for the isotropic harmonic oscillator, which is what we're using as our motion thing. Okay? So putting it together here, area of a triangle, angular momentum, that's constant. Also, equal area swept by radius vector in each time interval. Equal area, there's R cross dr, that's R cross v dt, okay? R cross v dt over 2, this thing, okay? Now that R cross v is L over m, okay? That's this guy right here. So this is L over m integral dt, which is time. Okay, so an equal, allow to fly a certain amount of time, then the area is going to be that. This is constant, and that, of course, is constant in non-relativistic mechanics. Okay? So, that's pretty neat. Now, in one period, okay, 1 over the frequency, that's 2 pi over omega, okay, what we can deduce from this, if that tau is the time, okay, is that you have 2 times m times that area. Area is this right here. Then it will be AV pi for the ellipse orbit, but these equations are true for any central force. Kepler's law applies to more than what Kepler was worried about. It applies to any central force. That's, I think, really, really important. And it's related to the area that's swept out by an orbit. Now, other objects that are not central forces are not likely to close like ellipses do. You're going to start out high and you may come right around and be low, but the area of that thing, whatever it is what we're talking about here, and it's as exact for that. So it's you know, we're getting, you know, nature's being kind to us and giving us more power to our theory than we might really think we deserve. Now, in lecture 8, we related omega to some constants. Don't forget that. That makes it easy to use this in various problems. Once you know the omega, you can determine the period and all of that stuff. Now, let's some Kepler laws that apply to any central isotropic force F of R, and we're taking these two examples. Okay, the difference between a Coulomb and an isotropic harmonic oscillator, I've already said the similarities are they make ellipses. And the difference is that for the Coulomb orbit, the center is at the focus of whatever conic section you're getting, and you can get hyperbolas too. But for attractive orbits, you can get ellipses. Okay, just like our attractive oscillator. This is a stable oscillator. This being used here, the isotropic harmonic oscillator. Okay, so same thing. The triangle area between V and R is constant. Okay, area of the triangle. Okay, it's just that the numbers associated with this, and this frequency I referred to before, gives the formula for our oscillator, our isotropic harmonic oscillator. But for the Coulomb, and this is derived in Unit 5, and you may have already seen it
sophomore physics or junior mechanics, but it is a function of A and B of the ellipse. Also, it's just that it's, instead of being the product of A and B, it's the product of B and the inverse square root of A. That's, we have to think a little bit about how that happened. Okay, nice comparison though. Okay, angular momentum, which is conserved. Okay, for our object, it's m alpha beta, and then here's that omega value. So again, it's a product of A and B, okay, just like this is, and this one is a product of inverse square root of A and B with that, you see. Now remember, we've got an oscillator here that's based on gravitational constant. The Coulomb orbits outside over there are going to look like that. Okay. All right. The mass of the Earth, by the way, is in the density. These are the properties of the Earth that make these formulas. Well, both of these require some extra thinking for the Coulomb orbit. Okay, an equal area swept by radius vector. Okay, all three of these work for any central thing, but these are the actual numerical values for one period. Okay, product of AB, product of AB, but with an A minus 1/2 B in the denominator. Okay, which makes this one a function of A only. The B's cancel. Okay, it's a function only of B. All right, that's the one period relationship between the period and the geometrical features. Only the A makes a difference. For this one, well, it's constant. Okay. No, the A and the B both cancel for that one. Okay. Now, when we come back in Unit 5, we're going to take oscillator derivation along with the Coulomb. So, if you want to read ahead, you can see what is going on here fairly. Let's do energy real quickly, and then I think we're done here. And the basic idea, talking about orbital energy, that's the sum of kinetic and potential. Here's where we're going to start using matrix quadratic forms again. We did it for the superball for velocity. We also have one for space. It makes potential. This is the kinetic, of course. So it's these things that we're going to be playing with tomorrow. Remember, the next lecture is tomorrow instead of Thursday. And this is the new guy on town. This is a quadratic form expressing spring energies. This thing is very simple right now. It's isotropic. It doesn't have any off-diagonal components. We talk about normal modes of molecules and things. This matrix will have 4 different numbers in it, possibly. The basic thing that we have is this, and we put in our values for velocity, squared x and y, and our position, squared x and y. Okay, that's from these things that we just did in the calculus discussion of the phasors, and that adds up to a constant. Okay, so what we're getting here is the energy of an oscillator is proportional to the square of the hypotenuse, that rectangle encircling the ellipse. A squared plus B squared, major diameter, minor diameter, summed and squared, times 1/2 angular velocity squared. That's pretty simple. Okay. KE plus PE, thing like that, where omega is, as we said, there. And just getting used to the notation is a little bit of this. Now the total energy function for these two is actually simpler for the Coulomb orbits. For the Coulomb orbits, the total energy is only a function of A, just like the period. That's kind of cool. Something you should look forward to learning about and maybe so much so you go look at Unit 5. But it is nice. This guy you need to know B. Okay, to talk about energy. So that's a real beautiful thing. Okay, I think we're about wound up here, but I do want to just start a little bit. We're going to be working with quadratic forms in both position and P. P stands for momentum. We'll be doing that too. Now this won't really get together most completely until we get to chapter 12. But chapter 11, I want to go through the geometry of this. I want to look at an orbit that has a position, and then there's going to be a perpendicular, that's what that can stand for, a vector that is obtained by taking the quadratic form for that ellipse and acting on the position R. So this is what we're going to learn next time. You might look ahead just so that the lecture makes sense. It sometimes helps to pre-study, and it's not as painful then. The lectures are easier to do. But the original ellipse equation, this thing, Q is just 1 over a squared and 1 over b squared on a diagonal of a matrix. Gives you x squared over a squared plus y squared over b squared. Well, that's r dot p, that's 1. That's kind of interesting. The inverse ellipse is just the inverse of the quadratic form for the perpendicular vectors. And they're called perpendicular vectors because they are perpendicular to the velocity. And that's true throughout the orbit. So these are some geometrical things that are true of our oscillator orbits, but they're true of the ellipses that we find in momentum space, in velocity space, in Lagrangian space, they become circles. But in the Hamiltonian and the Lagrangian, we have, as you know, Lagrangian ellipse is a tall, skinny thing. The Hamiltonian ellipse is a short, fat thing sitting horizontally. We got to put all that together with the orbits, you see. The orbits are all using the same geometry. So that'll be it for today. We've got enough to do tomorrow.